Hi, I'm Diego Navarro from the Stein Monogastric Nutrition Laboratory at University of Illinois, and I will talk about the effects of physicochemical characteristics of feed ingredients on total tract digestibility of dry matter, energy, fiber, and protein by growing pigs. In recent years, there has been an increase in the availability of co-products and byproducts of the oil and starch industries that can be used as feed ingredients in diets fed to pigs. Inclusion of these ingredients lower feed costs compared with using the traditional corn soybean meal diet. However, these ingredients are relatively high in dietary fiber content, and it's been shown that dietary fiber may reduce the digestibility of energy and nutrients in pigs, and this may be explained by the physical chemical characteristics of fiber. I will briefly describe the properties of fiber that are relevant to animal nutrition, and they include bulk density, solubility, water holding and water binding capacity, swelling, viscosity, cation binding capacity, and fermentability. However, we have to keep in mind that these physical chemical properties change as fiber progresses through the gastrointestinal tract. Bulk density is defined as the weight of particles divided by the total volume it occupies, and bulk density may be easily manipulated by feed processing. Solubility of dietary fiber is its ability to dissolve in solution, may it be water or dilute acid or base, or a buffer or enzyme solution mimicking the conditions of the gastrointestinal tract. Solubility is determined by the structural stability of the constituent polysaccharides of the fiber fraction. For example, linear polysaccharides that form ordered crystalline structures, such as cellulose, are likely to be insoluble, whereas nonlinear polysaccharides that contain branching in their structures, as seen in arabinoxylenes and mixed-link beta-glucans, are generally soluble. Water holding and water binding capacity are the amount or quantity of water bound to fiber without or with the application of an external force. Soluble fiber generally has a greater capacity to bind water than insoluble fiber. Swelling occurs when molecules are spread out by incoming water until they are fully extended or dispersed. This is important because it increases the surface area of polysaccharides for microbial action and fermentation. Viscosity is defined as the fluent's resistance to flow mainly due to the physical entanglement of the polysaccharides in the solution. And viscosity may affect digestion and absorption of nutrients by influencing the mixing, diffusion, and flow of nutrients in the digesta. Viscosity may also prolong gastric emptying and therefore increase transit time. Cation binding capacity is the ability of fiber, specifically its free carboxyl groups and uronic acids, as well as phytate and lignin, to bind and impair the absorption of bile acids and mineral ions such as calcium, magnesium, and zinc along the gastrointestinal tract. And lastly, fermentability refers to the microbial fermentation of fiber in the large intestine, which results in the production of short-chain fatty acids. Soluble dietary fiber is fermented in the cecum and the proximal colon, whereas insoluble dietary fiber is fermented slowly until the distal colon. Fermentability is highly dependent on water binding capacity and swelling properties of fiber. The objectives of this experiment was 1. To determine the concentrations of digestible and metabolizable energy and the apparent total tract digestibility of energy, dry matter, and nutrients. And 2. To determine the correlations between apparent total tract digestibility of dry matter and nutrients, concentration of digestible and metabolizable energy, and in vitro digestibility of dry matter of the same test ingredients as determined in a different experiment. 10 feed ingredients were used in this experiment, including 2 sources of cereal grains that are corn and wheat, 2 sources of oilseed meals that are soybean meal and canola meal, 2 sources of corn co-products or byproducts that are corn distillers dried grains with solubles, corn germ meal, copra expellers, and sugar beet pulp. We also included 2 synthetic sources of fiber that are sulcoflock or purified cellulose, and pectin to represent extremes of insoluble and soluble fiber, although these ingredients are not usually included in commercial diets fed to pigs. 80 growing barrels with initial body weight of around 48 kilos were used and placed in metabolism crates. Each period had a 19-day adaptation period, wherein the first 14 days were spent in individual barns, and the last 5 days were spent in the metabolism crates. This was followed by 5 days of fecal and urine collection using the marker-to-marker approach. The experiment was set up as a randomized complete block design with 10 treatments and 8 replicates per treatment. The 10 experimental diets included a corn-based diet, a wheat-based diet, a corn-soybean meal basal diet, and 7 diets with a corn-soybean meal basal diet, plus each of the 7 remaining ingredients. The ratio of the inclusion rate of corn and soybean meal in the last 7 diets are the same, so the contribution of corn and soybean meal can be calculated, and the digestible and metabolizable energy of the ingredients can be calculated by difference. This graph summarizes the concentration of digestible energy in ingredients on a kcal per kilogram dry matter basis. The digestible energy was greatest in soybean meal and is in agreement with published data. The concentration of digestible energy in the 2 cereal grains was not different from copra expellers because of the high concentration of fat in copra expellers. As expected, purified cellulose had the least concentration of digestible energy because this is purely insoluble fiber. The same trend is observed with the concentration of metabolizable energy. This graph summarizes the concentration of Me in the ingredients also on a kcal per kilogram dry matter basis. Soybean meal had the greatest concentration of metabolizable energy, and as expected, sulcoflock had the least concentration of metabolizable energy. Moving on to the correlation coefficients, this table summarizes the correlation coefficients between the in vitro digestibility of dry matter from the previous experiment using the same ingredients and the concentration of energy and apparent total tract digestibility of dry matter and gross energy in vivo. The in vitro apparent total tract digestibility of dry matter was positively correlated with ATTD of dry matter and concentrations of digestible and metabolizable energy, which indicates that the in vitro procedure may be used to estimate digestibility of dry matter and energy in vivo. The concentrations of digestible and metabolizable energy were also correlated with ATTD of dry matter and gross energy. Now we look at the correlation coefficients between fiber fractions and the concentrations of DE and ME and ATTD of dry matter and crude protein. On the first row, the concentration of total dietary fiber was negatively correlated with the concentrations of digestible and metabolizable energy, as well as the apparent total tract digestibility of dry matter. On the second row, the concentration of insoluble dietary fiber was correlated with the concentrations of NDF and ADF, and was negatively correlated with the concentration of digestible energy and the apparent total tract digestibility of dry matter and crude protein. On the third and fourth rows, we also observe a negative correlation between the ATTD of crude protein and the concentrations of ADF and NDF. This suggests that the concentration and type of fiber may negatively influence the digestibility of energy, dry matter, and crude protein. This next table summarizes the correlation coefficients between physical characteristics of feed ingredients and digestibility of fiber. On the first row, swelling was positively correlated with apparent total tract digestibility of total dietary fiber, insoluble dietary fiber, neutral detergent fiber, and acid detergent fiber. On the second row, water binding capacity was also positively correlated with ATTD of TDF and IDF. On the third row, viscosity was positively correlated with ATTD of IDF, NDF, and ADF. This indicates that physical characteristics may influence the digestibility of fiber, but there were no observed correlations between these physical characteristics with the concentration of digestible and metabolizable energy. In conclusion, we observed that the in vitro apparent total tract digestibility procedure may be used to estimate digestibility of dry matter and energy in pigs. And due to the stronger correlation, total dietary fiber may be a better estimate of the concentration of digestible and metabolizable energy in feed ingredients than ADF and NDF. We also observed that there were no correlation between physical characteristics of feed ingredients that we measured and the concentration of digestible and metabolizable energy. We also observed that swelling, water binding capacity, and viscosity were correlated with digestibility of different fiber fractions, but not with the concentration of digestible and metabolizable energy. And therefore, these physical characteristics may influence fiber digestibility, but not the concentration of digestible and metabolizable energy. I would like to acknowledge AgriFirm Innovation Center of the Royal Dutch AgriFirm for financial support of this project. Thank you for listening, and if you would like to know more about this topic or know more about nutrition in general, I would encourage you to visit our website at nutrition.ansci.illinois.edu.